So, I hope you all had a great day on the slopes. I
actually want to note that we should have had a ski meeting for a part much earlier. There's some serious ski talent in this room.
You make me nervous.
Introduction's a second.
Yeah, introduction is a second. So how it started, how I got into this performance tool analysis research. For me, everything started in 1990 in Vienna, where I started a PhD position with, under the supervision of Professor Hans Siemer. Some of you may still know him, and Michael Gerndt was also there for a couple of years. Siemer's group basically was working on compilers. At that time, I think you brought Superb, and I had to find my PhD topic. And it was kind of a struggle. Siemer really, gave me a lot of freedom, gave everyone freedom to find it, but it was really hard for me to find. Until the day Karl Solchenbach from Ballas came to the city. Solchenbach, I think some of you know him. So he came to the city of Vienna. We just got the first parallel computer in Vienna. Everyone was excited, a big crowd, more than 100 people, mostly scientific computing specialists, attended his talk, and he gave a presentation, I believe, on Vampire. And if it wasn't Vampire, it was a predecessor system. It looked very similar, if I still remember, to Vampire. And he gave this great talk. Here's something from '96 from Vampire that was more advanced than what I saw at that year in 1990, where he saw, he showed these snapshots, timeline, and then for every processor, an activity line, basically when it was computing, waiting, and communicating. And then I gave him a question at the end of the presentation and asked him, okay, you can see for this 32 processor, whatever that was, you can see when they communicate, and this presumably is some performance problem, but how do I find out where to pinpoint it in my application code? And he was not very amused about this question. I remember he was really kind of embarrassed. He answered something like this: well, we assume this Vampire is used by the application developer who uses at that time not MPI, but the predecessor system, what was? Yeah, something like this. And we assume these guys know where they put these send and receive statements. So this gave me the idea, and I thought, okay, if this is the case, that's certainly suboptimal. Wouldn't it be great to start a PhD where you kind of, determine performance problems and be able to pinpoint directly to the input code from where the performance problem is coming? This is really where I got the idea at that time. And the tool that then I built, I spent like an hour last night to find an old snapshot of the tool that I built. I had another problem. So Siemer was doing math, okay? And I thought, how can I do a PhD thesis with a tool that's similar, competing with Vampire, instrumenting code and counting events? There's no math in there. At least at that time I had no fantasy. So I thought I had to make it a bit harder. Let's do performance prediction. Because there I was sure, you need some theory, some model building, and I built a performance predictor at that time called P-cubed-T, which stands for parameter-based performance prediction. And it was one of the very few tools that actually was integrated in a compiler. It was at that time the Superb compiler. And I managed to do at the end of my PhD thesis, so I don't know if you can recognize, you see that there's loops, nested loops in there, and there's some intermediate representation of communication. This basically was seen by the application developer, and to the side you see this performance prediction information. So, and what I predicted was various parameters on communication, transfer time, number of send receives that have been invoked in there, network contention, even that was possible with static routing networks at that time. The systems were quite predictable from my point of view, work distribution, even cache misses, okay? That's what I created. And you see, I actually managed to really directly relate it to the input code, which at that time was kind of uncommon. So I still remember discussions with Al Meloni when he had the Tau, predecessor Tau, he was also far away from directly relating it to the input code. That all came later. So most of the time, performance tools showed you a signature, I don't know, maybe about call graph or individual functions and subroutines, but it was not possible. No one showed something, hey, this performance information is related to that loop. That took a while, but I managed to do that. That was my starting point. And now I switch back to the original set that I prepared. A little bit more history. So at the beginning, I worked with the Superb compiler, later a Fortran compiler, built this tool, and then I got my habilitation, had my own PhD students. I built more performance tools. Then was this Galea, which was a monitoring instrumentation tool. This was done by Hung Lin Trong, who also attended some of the APART meetings. He's now in Aalto University. Then, together with the student, we developed the Centurio tool, which is an automatic performance experiment generation tool that was done by Rado Prodan. And then there was a hard cut. So this was also during the APART working group time. Then there was a hard cut because the European Union decided to stop funding HPC. At least no HPC research. I don't know about infrastructure. That was like stopped at that time, my opinion, okay? And the official opinion that was communicated to me, they said we invested many millions of, I don't know whether the euro was there at that time, and we consider this now done after 10 years, okay? And then they stopped for like 8 years, a long time, and then a lot of groups kind of were lost in the space, and many moved to something like grid computing, some others somewhere else. I remember supercomputing, even John Kennedy, Dan Reed, and Dennis Gannon had this GRADS project. They also did grid computing, so I don't know whether in the USA they also had funding problems, but in Europe it was very hard. So then I jumped with my small team onto Ascalon, and so here it was Fortran. Then we switched from message passing shared memory to so-called scientific workflows. So these are, graph-based applications, mostly from the scientific area, that were executed on the grid, on a distributed system. And again, built some additional performance prediction analysis with other colleagues in my team. A bit later, we built a predictor for serverless functions, for instance, and tasks. So that was only about 5 years ago. So there's a lot of performance prediction work that we did. But the main focus, actually, I moved away from performance tools and started getting very much interested in runtime optimization, scheduling, resource management. This was really the main focus that I got involved at that time. And now we switch from Fortran to C, Java, Python. What I'm particularly proud about, that several of the guys that worked in my team, so I supervised the PhD thesis, actually now full professors. So Lin, for instance, is in Aalto University in Finland. Rado is professor in Klagenfurt, and Farouk is professor in Saudi Arabia. So some of this work kind of was the beginning of an interesting scientific career. And then I switched back to compilers when the funding started again. Then after like 8 years or so, I think IBM brought out this cell processor. All of a sudden, parallelism was everywhere. And EU kind of figured that out, and I thought they have to start fund this again. Then we also basically started with compilers for HPC. The compiler we started at that time called Insieme, target language, now C++. So Fortran we kind of dropped quite fast. And here we started with a compiler that were built mostly for OpenMP, but also for Silk. And some of the topics at that time were auto-tuning for multiple parameters. A lot of groups, I think even some of you here, did also very successful research on that. But performance prediction was always there. So if you worked on optimizing something, you needed some kind of performance model and measurement. That was always part of this research. Then the AllScale EU project started. So out of the Insieme compiler, we built the AllScale compiler. This was more like a high-level C++ domain-specific language. The main goal was to hide MPI that time, so productivity was high on our agenda. And I'm going to present some more details. This is the main focus, actually, of my talk. And this project is still going on in some way. But the latest project we have is a runtime system. It's called Celerity. That's the strongest project in HPC in my group. Here we target GPU clusters. So how to develop applications without knowing MPI, so it's hidden again, for arbitrary large GPU clusters. Philip will give a presentation, I don't know, on Thursday about this one. Productivity is very important. We are willing to trade in some performance, but the main focus is to hide MPI. We consider it's kind of complex to work with that. You may have different opinion, but this is what we are really interested in. And here the target language is not CUDA, but it's SYCL. But then there's other work, so we have like 2 teams. So we follow up this distributed systems research. We developed the Apollo application development runtime system targeting the edge cloud continuum. And again, the scientific workflow, so batch processing is important. Main interest, again, scheduling, resource management, usually always for multiple parameters, performance, cost, energy consumptions, things like this is what we are interested in. And the latest topic we opened for us is Apache Flink, because we are about to get involved in a data pipeline and big data project, but this I just, so I will not further go into any of these details. General observation from my point of view, so I spent much more time on scheduling, runtime optimization of parallel codes, but also distributed systems code. What I see by this community, if I look at the related work, competitors in scheduling, optimization, runtimes, libraries, compilers, usually they use their own little analytical models. They rarely use some of the tools that have been mentioned here. They do also use real-time measurements, but here I see more like platform libraries or PAPI or something like this. But for instance, I never met a group that uses Tau to drive a scheduler. Maybe Tau has not been made for that. That's my general observation from the scheduling runtime system optimization point of view. Of course, what we see for if you need more complex models, for instance, for resource management, then the people start using a lot of machine learning models. This is my point of view on performance analysis tools, techniques, in this area of scheduling and resource management. And now I would like to spend a bit more time, I think I still have like 20 minutes or so, on this AllScale project. So this is not about a performance tool, but it doesn't go back 20 years. We finished this project something like 4 years ago. It was very interesting because it was one of the few projects funded by the European Union that try to target a single programming model for heterogeneous distributed memory architectures without exposing MPI to the application developer. So again, productivity was in the main focus. And this was interesting work together with a couple of partners that we did. And this I would like to present here because it kind of closest to HPC. I don't want to bother you with distributed systems, even though it's not about a performance tool. So the motivation of the AllScale project was, I think that's still valid now. So you have shared memory nodes that are usually programmed with OpenMP, Silk, or something else. Then you have accelerators. So you have CUDA. But in these days, also SYCL plays a role, and then you have distributed memory clusters, which are mostly programmed with MPI. And then target architecture was heterogeneous systems that combined all these shared memory nodes connected by some fast network plus accelerators, and how to build applications for that. Okay, and I remember at that time most projects had like MPI involved, and what you saw at that time, and probably still at this time, mostly a combination of multiple of these programming models, so MPI plus CUDA plus OpenMP or something like this. Sorry.
Just a brief question. Thomas, could you please explain the semantics of those letters? So M I get is memory, C plus core. What is S and
on the right side there? On the right side?
On the right side?
It appears everywhere.
This FZ HPC?
No, the letters in your figure.
This is memory.
It's a dollar sign.
Yeah, and this is core. Yeah. Yeah, sorry for this simplified view. But target architecture, basically distributed memory systems with accelerators, okay? This is what we set out. And we saw at that time, and probably still at this time, it's mostly MPI plus CUDA, maybe plus OpenMP, so a combination of different programming models. And we wanted to do something different, okay? And the idea is this: if you couple like MPI with OpenMP or CUDA, once you switch from MPI to OpenMP, the OpenMP program doesn't know that there's an MPI program surrounding it. Every different program, every specific programming model lives in its own little universe, and one can assume that probably too little information is known by OpenMP from MPI, and when you go to CUDA, CUDA doesn't know it has been called for OpenMP, okay? So maybe there's a lack of information that goes across these different programming layers. And of course, it requires you to learn at least 2 different programming languages and not just 1, and maybe even 3. So that's an additional complexity. On these slides, you see every once in a while that a lack of support for auto-tuning, load balancing, monitoring. So here the idea is if you get some, I don't know, compilers from a specific vendor, there's limited support. You have to get external libraries or external tools that have been developed by others in order to back up your application development platform, and we wanted to have that in our AllScale environment as well. So the idea of this AllScale project was that you develop your applications at a high level of abstraction, right? Everyone kind of claims that, but we have a unified parallel programming model, and the user doesn't see MPI, and it doesn't see OpenMP, and it doesn't see any CUDA or anything like this. And then there's a tool chain. In our case, it was a compiler plus a runtime system. The runtime system was based on HPX, was taken over by a group in Erlangen. And the target architecture, is all these different architectures. So we didn't achieve the full set of goals and objectives. I have to admit at the very beginning, one of them, we never got to the point to extend this programming model to accelerated technology. This is why we had a follow-up project called Celerity, and Philip will talk about it in 2 days from now. And the other idea, so from where is this coming from? So basically we looked at Silk, which targeted shared memory parallel architectures and exploited recursive parallelism. And we were interested in AllScale whether we could extend the Silk idea to distributed memory systems. Okay, so we targeted basically recursive parallelism and tried to figure out whether this, could be a competitor to other existing programming approaches. So conventional flat parallelism, if you look at individual parallel loops, then you use a certain number of processors, and if you increase the number of processors per loop, then the work gets smaller and smaller, and at some point there's more overhead and synchronization than useful work. These red lines here correspond to global synchronization. This is coming from if you have multiple nested loops in a sequence. So in between, usually there's some kind of global synchronization. And then if you throw in more and more processors that should execute a parallel loop, at some point you see only red. Okay, it has an inherent tendency for large-scale parallel computers to have a lot of global synchronization in the most basic way. In contrast, recursive parallelism, again stimulated by Silk, has a tendency for large class of algorithms and patterns to have more local synchronization and less global synchronization. So recursive parallelism, of course, you start with a task and break it down into subtasks and so forth until you stop the whole thing. And here you see a typical picture. If you would measure the synchronization, the red line, or the red lines here, they correspond to global synchronization, but you see a lot of yellow lines here. And this is local synchronization. And the idea is that maybe for some classes of applications, targeting instead of flat parallelism, parallel loops, this recursive parallelism would give you at least the same, maybe even better performance. This is what we explored. Okay. The other thing that's of course interesting, if you work with recursions and need a lot of parallelism, I mean, this is exponential explosion. You generate tasks really fast. Okay, if you have a big machine with this technique, probably you have enough tasks to fill a large parallel computer. The other thing that was interesting, you have adaptable task granularity. In the last couple of years, a lot of people talk about task parallelism, how to support it. In a recursive task parallel model, you know, you are very flexible. You can stop the task here, and for others, you go down, make it more fine-grained. If something maybe goes out to a GPU, you can make it more fine-grained. If you stay up at the node level, you can make it more coarse-grained. It also kind of naturally maps to heterogeneous architectures. You know, at that level, you can think of put it on a single node, then maybe put it on individual processors, or at some lower level, at some point you go to accelerator technology. So it kind of, we had the feeling that this can be nicely exploited for the mapping phase, which is taken over by a runtime system, and also for resilience. If some of these nodes fail, probably has no impact on the other nodes. You just handle, you know, checkpoint or restart these individual nodes. So from this picture, we had a very good feeling that this would be interesting to try out as a competitor for these coupled programming models that are widely used in practice to create programs for heterogeneous parallel architectures. Then we also knew from a lot of papers, related work, that recursive task parallelism has a very good potential for these classes of algorithms, n-body rendering, stencil code, and so forth. There's a lot of papers out there that already showed. Okay, so we had this knowledge. Without that knowledge, I'm not quite sure whether we would have tried it. But as we knew we had good potential, this was reason enough for us to try it. And yes, now a couple of very basic slides. So this one here corresponds to some kind of workflow or call graph of a parallel program where you have individual task instructions, parallel sections, and so forth. And this one down there corresponds to the data. So from our point of view, many programming models kind of focus or try to simplify the creation of the parallel program or the control flow, or specify parallel loops, parallel sections. But then the handling of which task, section, loop iteration accesses what data usually is left to the programmer. So it's a bit more complex, but you may disagree. And then if you go to the parallel world, you have these parallel loops here, and then you somehow, both in shared memory and distributed memory, you have to make sure which task or which computation is accessing what kind of data, right, on your global data view. And that's kind of complex usually. The data distribution we consider the main target to simplify for AllScale. And in addition, we also wanted to basically improve on performance, portability, do some research on load balancing, resilience, and so forth. So we had kind of, except for load balancing, a limited success, but at least it was on the agenda of this AllScale project. Some efforts has been done, but it wasn't as successful as we decided it to be. And our idea was that the runtime system played a crucial role in order for this to effectively work, to achieve good performance. The runtime system we wanted to build or support had to have the control over distribution of work and data. Okay, I come back to that later on. And now this is the programming model that we support. First of all, it's C++. Okay. Then we offer, it's in some sense it's a C++, but a domain-specific language, because we offer specific operators 4 parallel loops. So you can use parallel loops, but we internally converted them to recursive task parallelism. We also offer parallel reduction, map reduce, stencils, and so forth, what most people are kind of familiar with, but at a high level of abstraction. So these are higher order parallel primitives. And then in order, for you to work with AllScale, you also had to use our own data structures. So we also offered C++ data structures as part of the AllScale platform for multidimensional grids, adaptive grids, maps, trees, and so forth. We could extend it. We just actually developed a couple of them in order to drive our 3 use cases. But an extension to well-known data structures from our point of view was quite feasible. So some of them we actually implemented and provided. So we had to use on the one hand under C++ our operators, but you also had to use our data structures. So it was not easy from an existing parallel program like in MPI to convert it. It really means you have to start from scratch in order to work with AllScale. Now, all of these operators here are internally converted to the prec for a parallel recursion higher order function. So all of that had to be converted to recursive task parallelism. And for this, we provided this higher order function called prec. And this basically, was a recursive task parallelism structure. These blue dots here are tasks. And you see here this recursive task structure, and this orange line corresponds to data dependence. So some task produced data that was used by another task, and this dependence, if you go on distributed memory, of course, we had to capture that. The other thing I already mentioned that for the mapping phase, this recursive task data structure kind of we found it convenient in order to do the mapping, because at a higher level was a mapping to a node, lower level to a socket, and then processing elements, GPUs, and so forth. We thought this nicely fit these heterogeneous architectures, and this I also mentioned, if there is a problem, an error with one of these tasks, you could, the basic version for resilience was checkpoint at restart. So that also, if something crashed here, doesn't mean that it had an impact on other tasks in terms of correct execution, but of course, it could have an impact in terms of performance. Then the data structure that we offer under C++, this is the application developer point of view. He really saw a global data structure. Okay, that's the dream since HBF, see a global data structure. And the runtime system internally knows which task in this recursive structure is responsible for which part of this global data structure. But this was only seen by the runtime system, and this was possible because the application developer has to use our data structures that we provided, depending on what structure you need, tree, DAG, arrays, and so forth. That's seen by the programmer. This is what the runtime system actually internally sees. And then the same for a DAG, for instance. This is seen by the programmer, and this is how the runtime system sees it. So these different data distributions are then basically used to map it to specific parts of your target infrastructure. And now I have a graph, and whatever data structure you need, internally, the runtime system, controls where the data is placed. The application developer doesn't have to deal with that. One of the most sophisticated analysis we developed as part of this AllScale, so we developed a compiler, was in this recursive task graph to determine which task requires what data in your data structure. Okay, and this was done by a compiler. This was really heavy theory. It was very difficult, but it was feasible because we actually didn't decide this completely at compile time. The compiler generates symbolic functions or expressions with some parameters, and during runtime, these parameters got filled in, and then you had basically precise information which part of the global data are required by what task. That was some of the hardest theoretic work that we have done as part of this AllScale project. Then a simple example for those of you who still may have a problem how all of that works. So if you have a loop that can be nicely executed in parallel, then in MPI, I'm just sketching, you know, you probably need some, if you code this up in MPI, you need a rank, you need a size. You probably have somewhere scattered to distribute the data to your processors, and then you have a parallel loop, and at some point you may collect the data. In AllScale, this is how this thing looks like. Okay, it's a P4, it's a high-level operator provided in C++. You have a lambda in there, you have an iterator range. This is all you have to write. And now you may think, well, in OpenMP, this looks very simple, similar, right? You have a parallel OpenMP loop, and that's it. But this thing runs also on distributed memory. That's the difference, okay? You don't have to worry about data distribution, which you have if you use send receive or many of the other programming models. If you use in this case, you had to use our array structure, then we did the data distribution automatically, okay? And internally, the whole thing is converted to this recursive task structure. That's also interesting because we believe this is important for various reasons, among others, a smaller tendency towards global synchronization. And a typical program that we have investigated during this project had multiple parallel loops, for instance. And multiple parallel loops, if you do it in a conventional way, usually you have some kind of global synchronization in between. But we did two things. On the one hand, we converted this operator as well as all the others that I have sketched at the beginning into this preg operator. That was a recursive task structure. And even more than that, we also started this recursive task as soon as the input data is available. So we didn't wait for this parallel 4 to finish before the next one started. As soon as the input data or the data required in order to do the assignment to B from the previous B4, this thing was ready to execute, okay? And handed over to the HPX runtime system. So this was one of the rare implementations that we have seen in practice that did that. It didn't wait for the first loop to finish. It started as soon as data is available, and another task in the next loop would be ready to execute. So kind of aggressive to exploit parallelism. This has been aggressively exploited by our system as well. So the platform contained the AllScale compiler and the HPX runtime system, which was extended, of course, in order to work with this system. Now, a few slides on the use cases that we actually handled. One was Amdados. This was developed by IBM Ireland. It's an AllScale simulation code that is a bit special because it's one of those simulations that actually use real-time data in order to correct the simulation to increase the accuracy. And this real-time data had some changes on the individual cells that got real-time data versus those cells that did not get real-time data, because this caused a load imbalance problem. So that was not easy to parallelize. And here you see the performance, one of the performance diagrams. So on the y-axis you have the number of subdomains that can be simulated per second. Okay, that's our performance metric. Here we have, you increase the number of cores. There was an MPI implementation of that, and the blue line is the AllScale implementation. And see, we pretty much achieved the performance of this MPI implementation, but you didn't have to code up MPI, you used the AllScale API. So productivity or simplicity, in our opinion, AllScale was better than the MPI version. Then there was another code provided by KTH Stockholm. It's a space weather prediction code, which essentially is a particle in cell simulation. And here, as you all know, if these particles move in specific areas, you have immediately a load imbalance problem. So it was not that trivial to code that up. Also not for the target architectures we considered. Again, the performance metric we show is the number of particles that can be simulated per second. And you see we also match the MPI version with AllScale, but we don't outperform it. And now the target systems that we were using at that time are a bit out of date, but 14,000 cores in Erlangen, another machine in Vienna with 32,000 cores. So it was reasonable tier 2 systems at that time. And now we show the throughput here again, the number of subdomains per second simulated. And you see the orange line is MPI, the blue line is the AllScale. The ideal performance would be flat, which none of them achieved, but at least here for Maggie, AllScale was doing a better job than the MPI version. Then the IPIC, the space weather prediction code, again, we were pretty close to MPI, but not quite as good. And on the Vienna supercomputer, again, we were doing a bit better than the MPI version. On the Vienna computer for IPIC 3D, AllScale was much worse than the MPI version. This, in our opinion, is not an inherent problem of our approach. We simply didn't have enough time to tune and improve the runtime system. Runtime system literature was finished in the last 2 months of the project, and we believe there's no inherent problem in there to improve this if we had a bit more time to tune it. But these were the raw results and what we measured, and at that time we just stopped it. But the interesting thing is, as I said, we set out we want to improve the productivity. Productivity means make it simpler, faster to code up codes compared to MPI plus something else. And here we used a couple of metrics, parallel lines, so the number of lines for the parallelization in the code over total lines of code. And there's another one, metric cyclomatic complexity, which is a bit more modern than just counting lines of code. Cyclomatic complexity basically reflects the number of branches in your code. And the more branches you have, the more complex it is. That's the assumption. And you see here in all cases, we outperformed, the AllScale version outperforms the corresponding MPI version, which is some kind of metric that we could use to show, hey, it's simpler to code up some of these applications by using AllScale than if you do it with MPI. But the performance is not always better, but at least we were kind of close, okay, towards the end of the project performance-wise. So that's the last slide I want to show. It's not about a performance tool, but one of the more interesting research projects we did, which was funded by the European Union. We tried to find a different way how to program heterogeneous distributed memory architectures by introducing this AllScale programming model. And the main idea was to hide this or to avoid a hybrid programming model by coupling MPI with something else and hiding MPI altogether. The hardest thing in terms of theory, theoretic work, was really building this compiler analysis that figured out what data is required by which task in this recursive task structure. Another very hard thing was really to build a C++ front end under LLVM. That was an absolute nightmare because we had to have our own intermediate representation. It was horrible. And a couple of other advantages we had here. There were other problems. It really required advanced C++ knowledge, in particular if you wanted to extend AllScale for new operators and new data structure. That is not trivial in this platform. Compile times were significantly longer. It didn't work for external libraries. If you included external libraries, AllScale had no impact. This was just run as is, but was not touched by the AllScale execution model. And we never really had time to extend this model for accelerators. And that was the reason then later on we started a new project called Celerity. There will be a talk about this on Thursday. Yeah, and with that, I close my presentation. Thank you for your attention. My glass. Yeah.
What do you think about accelerators? How challenging, dramatic is that going to be?
We never had time to think of how AllScale could be extended to it. But we have a new project that's we actively followed. We have like 7 people in our team that work on that. And here the idea is to extend SYCL a little bit by a few constructs because SYCL targets only single nodes with a couple of GPUs, but we developed Celerity, which targets basically an arbitrary large number of GPUs by extending SYCL. And here again, if you work with GPU clusters at some point, you have to use MPI, right? You cannot avoid it. And in Celerity, we completely hide that level. But here, the API developer, the application developer is involved in defining what data you access in your kernel and in your task. It's not automatic data distribution. But the effort is very reasonable. I think productivity is really interesting. And MPI definitely don't use it, and it's really working very nicely. So that's a follow-up system. Again, it's not a performance tool analysis work. We focus on SYCL because this, based on the Intel initiative, is very popular among the academic community. And here again, our interest is to bring it to a higher level of abstraction based on SYCL, which is kind of widely known, and then see how good the performance is, similar as we've done here compared to those applications that use CUDA plus MPI or SYCL plus MPI, something like this. Yeah.
I have 2 questions. One is, to which extent does your approach depend on the task parallelism being recursive?
Yeah.
So how important is the recursion? And second question is, to which degree do you exploit new parallelism features of C++, which they have been introduced with C++ 11, C++ threads, and all the abstractions surrounding threads?
Yeah. So the first question, you can convert a parallel loop into a recursive data structure. You have a set of iterations. That's one task. Then cut it in half. You have 2 tasks, and cut it into 4. So you have 4 tasks, and so forth. This is kind of straightforward. So most of these conventional parallelism you really can convert to recursive parallelism. This is not done. The application developer doesn't see any recursion. You use our operators. There is no recursion in there. This is all done internally. Okay. And we tried it out for trees, for DAGs, for lists, for parallel loops. It works very nicely. This has not been invented by us. It's known by literature, how this is done. Okay. Also, Silk has extensively exploited it, and they had great performance results. I don't know whether this explained this thing, but I couldn't now say any kind of parallelism that's out there can be converted to recursion. I'm not quite confident to claim that, but it's a large class of patterns, stencils, particle in cell codes where this is kind of a straightforward approach.
So the idea behind my question was, so instead of dividing the data recursively, you can basically also divide it in one step without being recursive.
Yeah, but we wanted to have this recursion because the recursion gives us tasks. And if you go to a bigger machine, you need more than 4 tasks or more than 1 divided just once, and then you have 2 tasks. But if you have a bigger machine and you want to get performance out of it, one goal is, where's my parallelism? And we do it through these recursions. And if there's no potential for it because the problem size is too small, your parallel loop has 4 iterations, okay.
I mean, you can divide the data in one step into very small pieces.
Yeah. Okay. Yeah, but this is also kind of an auto-tuning question, how you can do in one step, but maybe this is not the best way. So in one step, you then generate 48 tasks, but maybe you want to have 128 tasks, and there is some kind of heuristics in there, how deep we go into the recursion, and I think that's a more generic approach than just one step, because what does it mean, one step? Maybe you get it wrong, right?
Okay, that answers my question.
Yeah.
May I add something to this?
Yeah.
Also, one part of this project that we weren't really able to explore very well was resilience, because we didn't have access to systems where we switch off nodes or MPI runtime systems that allow you to keep your application running if ranks die. But the fact that we were using recursion and tree-based data structures allows us more dynamic freedom, where at runtime we can choose to re-decompose the data structure. If you do this fixed when you start the application, then you probably have a much harder time adapting to changing runtime conditions. Even though we were never able to show that in real life, but only in simulation. But still, that was one of the motivations there.
Well, there's one more question. He asked also what features of the latest C++ we used, because it has support for parallelism in there.
That could be a lengthy answer. We had two tool chains for AllScale actually. One was the standard tool chain that only uses C++ 14 compiler. You can use for local development on your laptop. It has parallelism, but only shared memory, and it uses C++ parallelism primitives in order to achieve that. And once you need distributed memory parallelism, you need data flow analysis, program analysis, and for that you need the AllScale compiler, and that's then the large tool chain with a couple of more dependencies. But also with that, looking just at shared memory nodes within the node, we would use C++ parallelism primitives. Just putting a API on top of it in order to get to the distributed memory.
So I'm interested. So I like it's very important, yeah, that we actually look at the high level and have this high level interfaces that we need. So a long time ago we worked on HPF, right? And the big problem with HPF was always if you cannot analyze the code statically, right? And typical example are these sparse data structures, sparse grids, finite element codes, all that. So what happens with your environment if you go into that?
Yeah, so I think for this irregular data structure, this also has its limit, but for the data, for irregular it has its limitations. For regular data structure it's pretty good because it works with symbolic expressions. Okay, and these symbolic expressions could be refined then by filling in the missing data at runtime. So it still has to be largely irregular if performance comes out of it. I actually believe even for irregular this would work, but the performance is probably not convincing.
So this particle in Zelda, right? Which is a sort of, it would be an example for an irregular code. Right? But if you look at the domain composition, so it's regular. So probably you exploited this, right? Yeah, because you saw the particles, if they move in a certain area, then the recursion is further refined. If there's less particles, the recursion stops at a higher level. And this was a very good example where we found this recursive task is very nice for this kind of irregular behavior. How you can control how many tasks you generate dynamically. Yeah. Did you apply any of these partitioning libraries or so?
No. That was really completely built from scratch in C++. Yeah.
So the runtime system again relies on MPI, right? And MPI is not very good at supporting the task-based thing. So did you find anything that worked particularly bad or well about doing MPI? Were you considering getting rid of MPI and going lower than that?
Now, I'm not exactly sure. Does HPX, did they actually use MPI? I thought they bypassed MPI. If I remember, HPX is...
Two runtime systems, one that does and one that doesn't.
Yeah, but I think the one we used is from Baton Rouge, and there was one guy, Thomas Heller, in Erlangen. I think they were very keen on not using MPI. Yeah. So now I cannot answer your question, what was in particular useful, because they used something else. Yeah.
So you said there's no support for libraries and you're just running the libraries. Are those libraries running in parallel mode or sequential mode?
They run in whatever, in their own universe. That could be an MPI code, but for us it's black box, more or less.
My actual question is, because we allow a lot of it depends on the developer to come up with the layout and how, and then you translate it to the physical memory.
Exactly. Yeah.
Right. But libraries themselves also has their own special layout and special memory requirements.
Yeah.
Do you see any interference? In
No, and I think the libraries we used, I think we never used one that were running in parallel, right? I think they all were serial.
Yeah, we didn't because we don't officially support it. You could use it, just that performance would probably suffer because you would oversubscribe the shared memory node where your library is running.
Yeah.
Or if it uses MPI, it'd be more than one node probably. So we have no control over the degree of parallelism. Functionally speaking, your program would run. Not functionally speaking, it would probably be much slower than it has to be.
Yeah.
The preferred way would be to have a sequential library call. We're not preventing anything else, but we're not guaranteeing any performance. We're also guaranteeing any performance otherwise.
Our runtime system doesn't know what's going on in there. If it competes for the same resources, it probably has a negative impact on the performance.
this is the question I was asking.
Yeah,
How much
yeah.
was there any change?
Yeah, yeah.
Thank you.
5:10. Finish up. Thank you.